All right, so let's look at this final set of problems having to do with rank 1 matrices. A equals V times W transpose. And in this case, these are both in Rn. V and W are linearly independent column vectors in Rn that are not orthogonal. Since they're both Rn and Rn, this is a square matrix. The column space of A is V because every column is a multiple of V. The row space is spanned by W because every row is a multiple of W. All right, so first question, what are the non-zero eigenvectors of A? Now what I meant to say, and what I should have said is, what are the eigenvectors of A that have non-zero eigenvalues? And so the only vector that can possibly have a non-zero eigenvalue is V, because the column space is parallel to V. So V is the only possible eigenvector with a non-zero eigenvalue. So this has non-zero eigenvalue. So sorry, let me do this. Okay. Okay, V has a non-zero eigenvalue. And then all vectors perpendicular to V are also eigenvectors. Okay. Or instead of perpendicular, let me say orthogonal, because that's the language we're using. Okay, so all vectors orthogonal to W are also going to be eigenvectors. Okay, but only V is the only one that can have a non-zero eigenvalue, because as I mentioned, V is the only linearly independent vector in the column space, and an eigenvector must be in the column space. All right, part B, show that A has n minus 1 linearly independent eigenvectors with eigenvalue 0. So any vector that's perpendicular to W is in the null space. And the null space has, so it has eigenvalue 0. Okay, all right. Now you can also say that the null space has and so I can also say the null space has rank n minus 1 because A has rank 1. Okay, so if it has rank n minus 1, then there must be n, so there are n minus 1 linearly independent vectors in the null space. Okay. Now what I'm writing out here, I should say, is I'm writing out very sketchy solutions. If you write them out, you should be a little bit more complete. I'm just trying to give you an idea of the solution. Okay, prove or disprove A is diagonalizable. Okay, so A has n minus 1 eigenvectors with eigenvalue 0, and it has one eigenvector with eigenvalue not equal to 0. So that means that we have n linearly independent eigenvectors, and it's diagonalizable. So why is this V linearly independent from the other? Well, because it's an eigenvector with a different eigenvalue. Okay, so if you have eigenvectors with different eigenvalues, they're linearly independent. Okay, so prove or disprove eigenvectors of A with different eigenvalues are orthogonal. And in fact, that's not true because V is an eigenvector, and it's not necessarily orthogonal to vectors that are orthogonal to W. If that were the case, then V would have to be along W. Okay, vectors that are orthogonal to W may not be orthogonal to V. Okay, because they may not be along the same direction. Okay, so we can actually get an explicit example. The example would be I could take V and I could subtract its projection onto W, and that would not be orthogonal to V, but it would be orthogonal to W. So let me just give that example. If I take, and how would you do the projection? So you would take V, I have to do it this way, V, whoops, where'd it go? V, oh, sorry, still not there. Okay, now we're there. V, and then you'd have to subtract the projection, so that would be V dot W. Okay, so and then we're going to multiply that by, we're going to have to divide that by something. We have to divide it by, so what do we divide by? I think we divide by the square root of the norm of W squared. So that would be the square root of W dot W. Okay. So I take, so that's the, and then I take here, multiply that whole thing by W. Okay. Okay. All right. So this vector here is orthogonal. Sorry, is orthogonal to, let's see, W, but not to V. Okay. All right. So that's a vector that would be in the null space, but it's not orthogonal to V, so it's not a eigenvector. So what was my point here? Sorry, let me recap my point. I've kind of lost my. All right, my point should have been this one here, since it's orthogonal to W. So it's an eigenvector so it's in the null space. And you can verify that it's in the null space just by taking the inner product of this with W. If you get that, you'll find out that you get 0. But it's not orthogonal to V. So it's not orthogonal to V, which is also an eigenvector. All right. So the eigenvectors are not necessarily all orthogonal. Okay. Show that A is symmetric if and only if V equals W. Okay. And now, in fact, this is impossible because I said V and W are linearly independent. But suppose we have this setup here, and we have A is symmetric. Suppose A equals VW transpose, and A is symmetric. Okay. And also the other thing is that, so if you try to do that directly, if you have A is symmetric, that means Wi Vj equals Wj Vi. That always must be true because this is the Ij component of, let's see, is that going to be Wv? Is that going to be W transpose V or V transpose W? Well, this is one and this is the other one. If you write out the Ij component of V transpose W, it's one of these, and if you write out the Ij component of W transpose V, it's the other one. And since it's symmetric, those two would have to be equal. So if A is symmetric, this must be true for all I and J. All right. So I can divide out like this. So in particular, I could set I equal to 1. And so I can get W1 Vj over V1 is equal to Wj. And so that means that Vj is proportional to Wj with this constant of proportionality. And that means that W is proportional to V, or W equals CV. Okay, all right. So this problem was not quite phrased correctly. It should be that W is equal to CV, not W equal to V. Now, if W is equal to CV, I can choose the two vectors to be equal because I can distribute the constant among the two vectors. But it's true that as long as W is CV, then this is symmetric. You can pull the C out, right? Okay. Now, so that A can be written as A equals Q d Q transpose with Q transpose equals I if and only if A is symmetric. Okay. So we do know that A equals Q d Q transpose for any symmetric matrix. That was proved in class. That was the spectral theorem. But you can also show that Q d Q transpose is symmetric. So that means that, so that gives you your if and only if. All right. So here we say that if A is symmetric, it can be written as Q d Q transpose. If A can be written as Q d Q transpose, then naturally it's symmetric just by taking the transpose of this expression, and you get the same expression back again. All right, so for a brief add-on, let me talk about this problem number 2. For the 8 by 8 matrix for hard wavelets, compute WA transpose and use your result to find WA inverse. Okay. So if you multiply out W8, W8 is kind of an extension of W4. W4 has, well, let's say, so you want to follow the same pattern of columns. So follow the same pattern as the columns of W4. So the first column is all ones. All ones. Okay, it's ones all the way down. The second column is half ones, half minus ones. It has 4 ones and 4 ones and 4 minus ones. Okay, and then the next column has let's see, it's going to have 2 1s, 2 minus 1s, and 4 zeros. So the third and fourth column, they both have 2 1s, 2 minus 1s, and 4 zeros. But the second one is kind of shifted. 2 minus 1s. So they have different patterns. First, the third column has 1 1 minus 1 minus 1 0 0 0 0. The fourth column has 0 0 0 0 1 1 minus 1 minus 1. Fifth column is 1 minus 1, and then the rest are zeros. Sixth column is 0 0 1 minus 1, the rest are zeros. Seventh column 0 0 0 0 1 minus 1, 2 more zeros. Last column 6 zeros, then 1 and minus 1. Okay, so if you didn't catch that, you pause the video, go back and slow it down, and you write down what I said. Okay. Now, if you take this matrix, you multiply the transpose of this matrix times this matrix, you will find that the columns are orthogonal. All right, if you take the transpose, that turns the columns into rows. If you multiply rows by columns, you get orthogonal. When you do the product, you get they're orthogonal but not orthonormal. What does that mean? It means when you take the transpose of W8 times W8, you get a diagonal matrix, but it's not the identity. However, if you get this diagonal matrix, you have W transpose W is equal to this very simple matrix. So all you have to do is take the inverse of the simple matrix and multiply both sides by the inverse on the left. Okay. So if you don't know how to do that calculation, then please, I invite you to come talk to me and we can talk about it. So here's my lightning review of all these questions. So again, if there's anything unclear about any of these problems, please feel free to talk to me and we can go over it more in detail. All right, thanks for listening.